last time, we saw that for orbital angular momentum, the L value can only take in positive integer value. Okay, so even though our analysis of the general angular momentum algebra, which, let me write it over here. Our general analysis of the angular momentum algebra implied that, the eigenvalue of the J squared operator can be either positive or can be either, the associated number J can be either positive integer or positive half integer. We saw that for the orbital angular momentum, by connecting it to translation on a circle, we saw that the angular momentum L, the total angular momentum L, has to be integer. Okay, and we also saw that for spin, not spin angular momentum, for spin, the eigenvalue S can be either positive integer or half integers. Okay. We also saw that, when S is, say, a positive integer under rotation, under 2 pi rotation, the state remained invariant. And this is something we called particles that behave such in this way are called bosons. Okay, so that's, but number one. Number two, we also saw that there are other particles. So this is for S equals to 0. So this is for this guy. Okay, this is for this guy. But we saw that under, say, 2 pi rotation, when S is half integer, so it's half or 3 halves or 5 halves, ... under a rotation, psi goes to minus of psi. And such particles are known as fermions. Okay, so this is what we did in the last time. So, for example, we can have some, let's talk about some examples of such particles from fundamental particle physics. So if you look at fundamental particle physics, so I'm not talking about atoms or molecules. I'm talking about the, the particles that we see in the LHC colliders and stuff like that, the most fundamental constituents of the universe. Okay, so for example, we can think of, say, S equals to 0. There is such a particle. Do you know what it's called?
No, sir, I don't.
Anyone else? You want to hazard a guess? Spin 0 particle? It's a very famous particle. It was discovered recently, although conjectured for many, many years, even before you were born.
Boson?
It is a boson, of course, because it's S equals to 0, but what kind of boson?
Higgs boson.
Exactly. So
Higgs
the Higgs
boson.
boson.
Yes.
So the Higgs boson, under rotation, its state remains unchanged, okay? And so if I take U, so this is under, of course, 2 pi, but if I rotate Higgs boson by some arbitrary amount, alpha, then the Higgs boson state is given by this, right? Because it has 0 spin and 0 z component of angular momentum. So, the general formula is that when U of alpha, where alpha is the angle that is the rotation around the z-axis, is applied to the field, we multiplied by minus I alpha m, m being the z component of the angular momentum. But here we see m is 0. So if m is 0, then for any rotation, this is just 1. This factor is 1, so we get 0, 0. So, the Higgs boson is kind of a more symmetric or spherical, most spherical particle, meaning that it's the same no matter which direction you look at. Okay, so it's a scalar particle. This is how a scalar behaves. Remember that when we took a p squared, that's a scalar object, and if you rotate p changes, but p squared doesn't change. So such objects are called scalars. So the Higgs particle is a boson, but it's a special kind of boson called scalar particles. And in quantum field theory, all particles are created by a quantum field. All particles are basically the excitation of a fundament of some quantum field. And so the Higgs particle it comes from a scalar field it's known as the Higgs field. Okay. Higgs was not the first person to think of the scalar field called the Higgs field, but he was one of the first people to apply it to fundamental particle physics. Of course, Higgs shared the Nobel Prize with several other people, so that's important to know. By the way, Higgs was the supervisor of the guy who taught me quantum field theory at Dhaka University. He's Higgs's student. So Higgs's student, his name was L.M. Nath, and he died a few years ago, and he's the one who introduced me to the subject of quantum field theory. So in terms of mathematics and physics genealogy, Higgs is my grandfather. Okay. Anyway, so enough of showing off. So that's a Higgs particle. And then spin-half particle. Can somebody tell me some example of spin-half particles?
Electron.
Okay, electron is one.
That's the only one I know, the obvious one.
From fundamental particle physics. Anyone else? Do you know electrons are part of a type of particle called leptons? And they're all spin-half particles. So leptons can be electrons. They can also be neutrinos. And they can be electron neutrinos. So electron neutrinos are neutrinos which interact with electrons. And neutrinos do not have any electric charge, but they're spin-half particles. They have tiny to no mass, and they only interact with the electron through the weak nuclear force. So they're extremely hard to observe. And then electrons have their heavier cousins, such as the muon. And muons can be detected in cosmic ray showers. So they're basically electrons, but heavier. And muons also come with their own neutrinos called muon neutrino. Not neutron, neutrinos. You should look at the value of muon's magnetic moment is a controversial issue, and now there seems to be some new data coming out which may lead to new particles. So you should follow that news. And then there is that tau neutrino, or the tau muon. Is that, I think it's a tau, yeah, tau particle. Yeah, it's even, is that tau? I mean, I forget the name. Leptons, yeah, tau. Yeah, that's a tau, particle, and then the tau neutrinos, okay? So these are some examples of fundamental spin-half particles, but they're also inside the proton and the neutron, there are also quarks. So quarks, although we don't see them outside the proton and the neutron, but there are quarks. Quarks are also spin-half particles, okay? So lots of spin-half particles in nature, but only one spin-zero fundamental particle, the Higgs particle. And then we have spin-1 particle in nature. Can somebody tell me spin-1 particles, examples of spin-1 particles, fundamental particles?
Are those like neutrons, protons? Those
No,
kind
fundamental
Sir,
particles.
gluon,
Oh,
Yeah, gluon, good.
photon.
Photon, yes. Do not forget light, photon. What else? So gluons are the particles which bind the quarks together. The quarks interact with each other through gluons. Okay. Photons are spin-1 particles, which is used for electrically charged particles to interact with each other. So do you know the particles which mediate the weak interaction, what they're called? Well, photon is one of them, but there are three others. They're called W plus, W minus, and Z bosons, okay? And they're heavy particles, they are massive, okay? They're massive. Gluons are massless, but you don't really see gluons like photons. Photons are massless too, but you don't really see gluons outside the proton and the neutron. So, but we can infer their existence from experiments. So is there anything higher in the realm of fundamental particles, something with higher spin?
I don't know, really.
Well, let's see if we have taken into account all the fundamental forces, right? So electromagnetism, right? So the electromagnetism, the force carrying particle is photon. Okay, strong nuclear force. The force carrying particle is gluon, or gluons, the loss of gluons, different types of gluons. And then there are the weak nuclear force. Those are W plus, W minus, and the Z boson. Are we missing a force?
Gravitational force.
Exactly. So gravitational force is conjectured to be carried by graviton. And graviton has spin 2. You can show that because if it's spin 2, it's an attractive force. So starting from, and that's something you have to learn quantum field theory to be able to show, is that starting from the quantum mechanics of these particles, you can show what the classical potential they will generate. Okay. So here it's an inverse square law. It can be either positive or negative, or attractive or repulsive. Here it's also an inverse square law, but it's always attractive. Okay, so that was basically a bit of the particle zoo.